Welcome to the massive open online course on fluidization engineering. Today's lecture on analysis of frictional pressure drop in fluidized bed by different models. So, in the previous lecture we have discussed how to estimate the frictional pressure drop in 3-phase fluidized bed, and also we have given example that what would be the different contribution of different portion of frictional pressure drop and also total pressure drop that has already been discussed and also given example. Now, in this lecture how to analyze this frictional pressure drop by the different models. These models may be correlation models from the basic, or there may be some mechanistic models. So, let us see what will be the different models by which we can analyze the frictional pressure drop in the fluidized bed. So, for this analysis different models, of course, the models will be based on the concept of two-phase flow. Considering two-phase flow of the gas liquid solid system, as in this case liquid plus solid mixture will be considered as a slurry phase, and it will be considered as a phase 1 and which is heavier phase, and gas that will be considered as a phase 2, that is lighter phase. So, 3 phase will be converted to 2 phase just by considering liquid and solid mixture as one phase and gas as another phase. And there are several models to analyze the frictional pressure drop in 2-phase flow. Lockhart-Martinelli model is the basic model that is developed 1949, and based on this concept of Lockhart-Martinelli model, now what should be the frictional pressure drop, or what should be the what should be the frictional pressure drop if we know the single phase pressure drop inside the bed. So, if we know this frictional pressure drop of this 2-phase pressure, in this case 2 phase means here what? Slurry is the one phase, gas is the another phase. So, frictional pressure drop of this 2 phase, that means in the 3 phase of this fluidized bed, then you can write this frictional pressure drop of these 3 phase will be is equal to phi SL square into delta P of FOSL. What does it mean? This delta P FOSL is nothing but the frictional pressure drop of the single phase slurry, and phi SL is nothing but the the multiplication factor or Lockhart-Martinelli multiplier for this slurry phase. So, if we multiply this multiplier of this phi SL square to the single phase pressure drop, then you can have this 3-phase pressure drop. Even if you consider the single phase pressure drop of gas, then what should be the multiplication factor by which you can get the total frictional pressure drop in the bed. Now, this you have to remember, this Lockhart-Martinelli model is basically for the frictional pressure drop analysis. So, this delta P FTP based on the single phase of slurry, what if you multiply it by this phi SL square, you will get this 3-phase pressure drop. Even if you multiply this phi G square, this is the multiplication factor of the gas phase to this single phase pressure drop of gas, then you can get what should be the total pressure drop, total frictional pressure drop inside the bed. Another parameter of this Lockhart-Martinelli model is X. What is this X? X is nothing but this multiplier ratio of this gas to slurry. So, in this case it will be equal to root over of delta P FOSL by delta P of FOG. So, in this case the frictional pressure drop due to the slurry and due to the gas. So, this x is nothing but the root over of ratio of this frictional pressure drop of single phase slurry and the single phase gas. So, from this you can get the total frictional. Now, this phi SL is the parameter and x is also one parameter. These are Lockhart-Martinelli parameter. Now, from this Lockhart-Martinelli parameter you will be able to calculate the frictional pressure drop. Now, how to obtain this phi SL, this multiplication factor or this parameter x. Now, different investigators they have developed the different correlations based on the different operating variables from the two phase operation in the bed, maybe in the bubble column reactor, in the slurry bubble column reactor or any other two phase system. They have actually calculated this frictional pressure drop and they have developed the multiplication factor and the Lockhart-Martinelli parameter based on their experimental data. Now, to calculate this multiplication factor, of course, you have to know some parameter here. What should be this x parameter, that is Lockhart-Martinelli parameter, and for this you have to know the frictional pressure drop of single slurry phase. And for this you have to calculate this frictional pressure drop of the single phase by the Fanning equation like this here. So, it will be rho into rho 0 f 0 u 0 square delta z by dc. What is this rho 0? Rho 0 is the single phase density, f 0 is the single phase frictional pressure Fanning friction factor, u 0 is the single phase velocity and delta z is the effective length of the gas liquid mixture inside the bed, and this is the column diameter or bed diameter. And this f 0 is equal to 16 by R 0 if it is laminar flow. If f 0 is equal to 0.079 by R E 0 to the power 0.5, Reynolds number to the power 0.25, this Reynolds number will be based on the single phase and it is for turbulent condition. So, this is for laminar condition and this is turbulent condition and this is for transition. That means, a laminar, if Reynolds number of single phase is less than 2300 and if turbulent flow, that means, if Reynolds number is greater than 4000 or the transition flow means here the Reynolds number in between these 2300 to 4000. So, you can calculate this friction factor this if your operating condition is in the laminar flow or in the turbulent flow or in the transition flow. Once you know this Reynolds number, you will be able to calculate this friction factor at different operating conditions. Now, this phi SL, Sisson he has actually developed this phi SL square, that means, here multiplier Lockhart-Martinelli multiplier here or two phase multiplier, you can say that this will be a function of x. X is the Lockhart-Martinelli parameter. This is nothing but the root over of ratio of frictional pressure drop of the single phase of liquid to gas, or here in this case slurry to gas. And here another one parameter is C. This is Sisson parameter, So, this is actually again you have to calculate or you have to obtain from the experimental data just by fitting this equation by the experimental data. Now, how to actually obtain this C here? See, if you know this x by this frictional pressure drop of single phase, and if you know this phi SL square, how to know this phi SL square? Because you know this total pressure drop delta P of FTP 3 phase flow, and if you know this delta P of SL single phase flow, then this is the ratio, and this ratio is defined as phi SL square. So, this is your experimental data and this is your of course experimental data. So, from this experimental data, or you can get the single phase flow from the Fanning equation. if you know this and if you divide these two pressure drop, or if you are getting this ratio, this will be represented as phi SL square. So, this phi SL square, this is known by the experimental data, and then x is also known from the Fanning equation and from the pressure drop, and then if you fit this phi SLS versus x here, maybe this from this graph here, if you are drawing or if you are plotting this data as this x, then you will get this type of relationship. If you are fitting this, you will get this what is that C value from this equation. So, just by least square method you can fit this equation, then you can get what should be the value of constant this C. So, you can use either this single phase slurry, or you can use gas phase single phase gas phase, from which also this phi g square you can get or you can relate this pi g square with the x as 1 plus C x plus x square. So, here again the same C x will be obtained. Now this C depends on whether this laminar condition, turbulent condition or transition, that depends on how you are calculating this F also, and also your operating condition. Another also system they had given, or that x square, this Lockhart-Martinelli parameter is a function of the ratio of liquid to gas mass flow rate, and then the density ratio of gas to liquid, and the viscosity ratio of liquid to gas here. And this lambda and A, B, C, those are constants that can be obtained from the experimental data. Now, x you know that x you can calculate from the experiment also. How to get this? If you do the experiment on the single phase, then what should be the pressure, frictional pressure drop, and if you do the experiment with the single phase of gas, then also you have to have the measurement data of the. So, from this measurement you can calculate this, otherwise you can calculate what will be the Fanning equation. So, you can get it from Fanning equation also, this relationship. Once you know this x, once you know this C, then you will be able to calculate what should be the phi SL square. Once you know this phi SL square, then you can easily calculate what should be the total frictional pressure drop just by multiplying this phi SL square to this single phase pressure drop of the slurry. So, from this equation you will be able to calculate how to, or you can analyze what should be the frictional pressure drop of this 3 phase flow. So, this is one way, this is Lockhart-Martinelli model. Based on that you can analyze this here. Now, if we know the experimental data, what actually to be known, what actually to be find out, you have to find out this C value. If you are just if you are fitting this experimental data with this type of equation, then you have to obtain this parameter C, that is one coefficient, this is unknown parameter, this will be obtained by the experimental data, and just by fitting with this experiment. Otherwise, you can directly correlate with the different operating variables by dimensional analysis, and you will get different groups, dimensionless groups, and then you just correlate with this phi SL square, and then you can get the phi SL square. Once you know this phi SL, you can calculate the total frictional pressure drop here. Now, Bankoff 1960 he has developed another correlations based on this Lockhart-Martinelli concept. Here they told that this 2 phase frictional pressure drop, or in this case here 3 phase frictional pressure drop, by just considering the liquids solid as one slurry and gas is in another phase. So, in that case he has proposed one correlations that this single phase pressure drop, if you multiply it by this factor of phi Bf to the power 7 by 4, then you can get this total frictional pressure drop inside the bed. So, this phi Bf is nothing but the multiplier of Bankoff. So, Bankoff multiplier. So, it is called if you are calculating this Bankoff multiplier from the experimental data, and if you are correlating this experimental data with this model of this phi Bf, Here this phi is a function of x, x is nothing but what is that mass quality of the phases. This mass quality of the phases here, x will be equal to here mass of gas by mass of slurry. Slurry means here liquid and solid mixture. So, x and here gamma is one parameter. This gamma again is a function of this density ratio of gas to slurry and also this mass quality of the gas slurry mixture. So, here you have to calculate now, you have to find out now what should be the gamma value or what should be the C1 and C2 coefficients for this gamma. The C1 and C2 are the coefficients which will be found out from the experimental data. So, these coefficients C1 or C2 are unknown parameters here. If you feed these parameters and by optimization method or by least square method, if you feed this data with the experimental data, then you will be you will get this C1 and C2 parameters. Now, how to do this? Only thing, this one is known to you, this is experimental and this is also experimental, then this divided by this you will get this phi b f. So, phi b f you can get, you can correlate this phi b f to this model here, and x is known to you, only gamma is nothing but C1 C2, and this C1 and C2 you have to obtain from the just by fitting with experimental data. Another model is Baroczy, Baroczy 1966 model. Here in this case they have introduced property index like IP in terms of viscosity and density of the phases. So, they have defined this property index as the ratio of viscosity of slurry to the gas here, and also the ratio of density of slurry to gas. So, here they have defined this as like this mu SL by mu g to the power 0.2 by rho SL by rho g. Now, based on their concept, they proposed that this 3-phase pressure drop or 2-phase pressure drop will be is a function of this property index and the function of single phase pressure drop. That means, if you multiply the single phase pressure drop with this function of property index, then 2-phase or 3-phase frictional pressure drop you can get. Now, then 1 by IP will be, then from this you can get it just this divided by this this is single phase pressure drop to the. So, 1 by IP is related to this here single phase pressure drop of gas to the single phase pressure drop of slurry. So, again you have to find out what should be the function of this property index from the experimental data. So, this one is your experiment, this one is your experiment, and then what should be the FIP, and then again this FIP that you have to model, that you have to make one correlations for this IP in terms of different operating variables. Now, these operating variables will be maybe what is that geometric variables, maybe physical properties, maybe some other what is that thermodynamic conditions. There are different operating conditions that will give you the change of this IP. Another model is the Wallis 1969 model. What happened here? They have also developed one correlation based on that Lockhart-Martinelli concept. Again this multiplier here, phi w is one multiplier concept. This phi w is the multiplier of the single phase pressure drop. Then you will get this 3-phase or 2-phase pressure drop here. Then you have to correlate this phi w square, that is here multiplier as a function of this mass quality of the gas and also density of the slurry, density of the gas, viscosity of the gas. So, in this way these correlations. So, if you know the slurry density, if you know the slurry viscosity, if you know the mass quality of the gas and other physical properties, then you can directly obtain this equation. And then if you substitute this, you will see if you multiply this single phase slurry frictional pressure drop and multiply this multiplier, then you will get the 3 phase pressure drop. Now, these correlations actually predicts the frictional pressure gradient well for the annular flow pattern. So, if there are any annular fluidized bed, you can apply this Wallis model to predict or to analyze this frictional pressure drop of this 3 phase flow inside the bed. Chawla 1972 he has developed the same concept of this frictional pressure drop by considering the multiplier as phi Chawla, and in this case they have correlated this phi Chawla as this mass quality, and one parameter is called here this S, that is slip parameter. This slip parameter is defined as 1 by lambda into this is a function of Reynolds number of gas, Froude number of mixture, and the density ratio of slurry to gas and the viscosity ratio of slurry to gas. So, in this case here this parameters is very important. This parameter depends on the different operating conditions, and here this Reynolds number of gas is defined as m dot g dc by mu g, whereas Froude number is this total mixture flow rate square divided by g dc into rho m square. So, by this Froude number is defined. If you know this Froude number, you can calculate, and if you substitute here and if you are making correlations with the experimental data with this S, then you will be able to calculate what should be the total frictional pressure drop. Now, what is that here? In this case, this phi Chawla to be obtained from the experimental data, and then just fitting with this model with this experimental value of phi Chawla, and you can get this value of S and which is correlated directly with the physical properties and the geometrical properties and other operating conditions. And this of course, this del p by del z or dp by dz of gas single phase, it is very important. In this case, Chawla has taken a single phase pressure drop of gas, and that can be obtained by experiment either, or you can calculate it from this Fanning equation of this. For that, f g is required. That f g is a function again Reynolds number. If it is greater than 2300, of course, it will be transition. If it is greater than 4000, it will be turbulent, and if it is less than 2300, of course, you have to consider that laminar flow regime, and based on which you have to calculate this gas phase pressure drop. Now, Friedel 1980 he has also developed based on the same Lockhart-Martinelli concept. Here again he has taken this frictional pressure drop of single phase pressure drop, and he has multiplied this multiplier of phi Friedel and to get this total frictional pressure drop. Now, this multiplier, he has proposed this correlation of this this multiplier into two components, like is one E, another is the here like this lambda into f g by Froude number and Weber number to the power this. So, according to this, what should be this E and lambda? E and lambda both are two parameters. Here in this case, E is directly related to this ratio of the slurry to the gas density and the friction factor of gas to slurry, and also it is the mass quality of the gas. It is seen that this E value is increases if increases, E value is increases if mass quality is decreases, decreases. Whereas, if it increases, so for the same mass quality, if increase there the density of the slurry, then of course, this E value will increase. So, this E is the one component which will be contributed by this property of the fluid, and what is that friction factor of the panning. Another important is that here lambda into Fg, F is defined as 1 minus x to the power, here this F is directly related to this mass quality of the gas, and G is the function of ratio of slurry to gas density, ratio of gas to slurry density, and the viscosity of the viscosity ratio of gas to slurry here. So, G can be calculated from this correlation, F will be calculated from this correlation, and F R m, that is Proud number of the mixture, will be defined as this. Weber number is defined as m dot T square into dt by sigma rho m, and rho m will be defined as this x by rho g plus 1 minus x by rho S L to the power minus 1. So, this will be the mixture density of gas and slurry. So, once you know this E, F, G and Proud number and Weber number of the slurry, you will be able to calculate what should be the multiplier factor of this Friedel, then multiply this multiplier with this single phase slurry pressure drop, you will be able to calculate what should be the frictional pressure drop. Then you have to compare with the experimental data of your own experiment to this friction factor, then how much deviation from your experiment to this model you will be able to calculate. If it is any modification of this model is required based on your experimental data, you can also do just by fitting this unknown parameter with your experimental data, or you can directly correlate this F R D, that is phi F R D to your in terms of your different operating variables just by dimensional analysis, and then fitting with the experimental data with these different dimensionless groups, just by having the dimensional analysis and fitting with the experimental data with these dimensional groups by regression, multiple regression analysis, you can easily obtain the or you can easily predict the multiplier of this Friedel. Another model is Garrett and Joshi model. Actually, they have analyzed the frictional pressure drop, and they have suggested that this total frictional pressure drop in this 3-phase system or 2-phase system based on the two contribution. One is single phase frictional pressure drop, another is the pressure drop due to the additional turbulence that made by these other phases. One single phase and then pressure drop will be developed by turbulence like this. If is there any bubble system, then of course this bubbly system bubble will just gradient will enhance the turbulence. Even some other provisions, if it is made in the fluidized bed, some other like intensification of the bed by providing other devices like baffle or other internal devices if erupt in the bed, then additional turbulence may produce, and because of which this frictional pressure drop will change. So, they have considered those additional turbulence by this delta P f AT, AT means additional turbulence here. So, this frictional pressure drop will be in the single phase frictional pressure drop without turbulence, and then if is there any turbulence made by the different provisions, what will be that frictional pressure drop. Now, this single phase frictional pressure drop you can obtain it from the Fanning equation. This is simple, this Fanning equation here, this is the Fanning friction factor again to be calculated from the what is the Blasius equation, and then additional frictional pressure drop, that is by additional turbulence, that will be calculated in there. In this case F AT, that means friction factor due to this additional turbulence will be is a function of that is the concentration of the solid, concentration of the slurry inside the bed, and this will be is equal to this FTP, that will be is equal to FSP by epsilon SL square, that is the volume fraction of the slurry, and this FAT. This is the friction factor due to the additional turbulence. Now, you have to you have to calculate this overall friction factor from the mixture velocity of the fluid inside the bed. Then what is the overall friction factor, from which if you know this single phase friction factor and the slurry concentration, what should be the friction factor by this additional turbulence, just by fitting this equation here. Now, you will see that overall friction factor will change here like this. If you are changing this epsilon S L, and if you get this overall friction factor as this, then you will see there will be data like this here. So, this type of equation straight line you will get. Now, from this straight line you will see here 1 by epsilon S L square if you are considering, then here F S P will be your slope, and then F A T will be the intersection that will give you your F A T. So, from this analysis of this overall friction factor from the experimental data, you will be able to calculate what should be the friction factor due to this additional turbulence. Now, this additional turbulence actually depends on the velocity fluctuation inside the bed. Now, that velocity fluctuation may be in the y direction, z direction or x direction. If your fluidized bed in the in such a way that your y directional velocity fluctuation is the dominant one, then this F A T, due to this dominant velocity fluctuation of this y direction, it will be u dashed y by u s. What is this u s? U s is nothing but the solid velocity, and here this is the fluctuating velocity at the y direction. Now, for heterogeneous flow, you will see this u y dashed, that is turbulent velocity, or you can say velocity fluctuation due to this turbulence, and it will be equal to u y dashed will be 1 by root over 3 into g L into u s g minus epsilon g u s L by epsilon s minus epsilon g u s to the power 1 by 3. This is actually, in this heterogeneousness, this fluctuation velocity will be obtained from the energy balance. So, this energy balance will give you this this fluctuating velocity. Now, this fluctuation velocity again is a function of u s g, that means superficial gas velocity and superficial liquid velocity. Of course, there will be, if it is a slurry system, you have to have the concentration of the liquid inside the bed, and also what would be the solid velocity inside the bed. And then this L is called this mixing length inside the bed, within which range of this fluctuation will be there, and then it will be defined as this sum lambda into dc. It depends on this column diameter or the bed diameter. This lambda is a parameter which is a function of again this slurry velocity, and then volume fraction of the gas and the gas velocity. So, from this correlation you will be able to calculate this I value, and from which you will be calculate this mixing length inside the bed, and from this mixing length you will be able to calculate what will be the fluctuating velocity or friction velocity. You can say sometimes it is called friction velocity, sometimes it is called fluctuating velocity, sometimes the turbulent velocity. And then from this turbulent velocity and the solid velocity inside that bed, you will be able to calculate what will be the friction factor due to this additional turbulence. Now, this additional turbulence, if you calculate from this here the overall friction factor, and if you are messing with this, if it is unknown parameter here lambda, you can directly obtain from this overall friction factor, and if you can correlate again with this liquid velocity or slurry velocity or gas velocity here, you will see what will be the deviation from this. If there is a significant deviation, then you have to modify this model by just fitting the experimental data and having this coefficient different from modification. So, in this way you can analyze what should be the friction factor inside the bed due to this fluctuating velocity and also additional turbulence. Now, for homogeneous flow, this u dash y, that means here fluctuating velocity is directly related to this effective velocity of the solid. So, it is seen that this is 1.5 times of this effective velocity of the solid, and this US solid velocity will be this is called sometimes sleeve velocity, and it will be represented as this USG plus minus here USL. This USG is the USG by epsilon is the actual velocity, and USL by 1 minus epsilon is called actual liquid velocity. So, from which you will be able to calculate this US velocity relative velocity or slipping velocity, sleeve velocity. This sleeve velocity will give you the fluctuating velocity in the homogeneous mixture, and then phi L square to be calculated here, this two phase friction factor to this single phase friction factor, and this two phase friction factor will be equal to single phase friction factor, and this friction factor due to the additional turbulence, and then this is what this friction factor due to this single phase. Or you can calculate this multiplier of this single phase slurry phase, that is in terms of the concentration of the slurry and the friction factor of this additional turbulence to this friction factor of single phase flow inside the bed, and also what would be the ratio of a slip to this single phase slurry phase. So, you can directly obtain this multiplier of this slurry by this correlation. Another way to calculate this in terms of this fluctuating velocity like this here one terms is that US by USL, instead of US by USL here it will come only the fluctuating velocity to the slurry velocity here. This is fluctuating velocity instead of US here. So, you can calculate this phi SL here. So, for more details you can get this different frictional pressure drop to analyze and to predict from your experimental data from these two books, from these books here, this Cooney and Levenspiel books you can follow, and also this fluidization and fluid particle systems that is by Young 2000 even you can get more information about the different correlations models given by me, that is your hydrodynamics and transport process of inverse bubbly flow. Here there it is the extensive actually analysis, extensive way that is represented of different frictional pressure drop correlations that you can get more information from these relationships. So, we can obtain from this lecture that how to analyze the frictional pressure drop by Lockhart-Martinelli model, how to analyze this frictional pressure drop in the fluidized bed by Friedel model, by different other models also. In this case you have to take care of taking the concept of this Lockhart-Martinelli, which is actually basically for two phase flow. Here we can apply this two phase flow for three phase operations only just by taking this liquid and solid as one phase and gas is another phase, because this Lockhart-Martinelli concept basically was from the flow of horizontal flow of gas and liquid. So, here instead of liquid we are considering this slurry of liquid and solid, whereas in the horizontal flow we are considering the vertical flow. Of course, all the parameters whatever these Lockhart-Martinelli parameters, multiplication or multiplier, Lockhart-Martinelli multiplier you can say, or two phase multiplier or three phase multiplier, different investigators they are naming in different way. So, these parameters will be obtained from the experimental data of three phase flow. Then once you know this three phase flow of and three phase frictional pressure drop, just by analyzing with this concept of Lockhart-Martinelli model, you will be able to predict the three phase frictional pressure drop at different operating condition. Also by this frictional pressure drop correlations, you can scale up the system of this fluidized bed with different operating variables. Of course, this variables or you can say parameters, Lockhart-Martinelli parameters, that is fixed, that is ratio of frictional pressure drop of that is slurry to the gas, and but the multiplier that is obtained, that you have to make a correlations in terms of different operating parameters. It will be better just by regression analysis with the different experimental data and making a general correlations for this, and then you can apply it with different operating conditions. Even after without doing experiment, you can calculate the what should be the frictional pressure drop by that model. So, I think it will be helpful to calculate this 2-phase and 3-phase frictional pressure drop by different models. And so, up to this we have discussed this liquid solid frictional pressure drop, gas solid frictional pressure drop, even gas liquid solid frictional pressure drop in fluidized bed. So, next lecture onward we will be discussing what should be the actually mechanism of distribution of gas inside the bed, that will be discussed, and how this distributor actually play important role for different hydrodynamics parameters. So, thank you for this lecture.